Hi everybody, welcome at the Aerial Robotics Working Group meeting of June 7, 2023. And this meeting is of the type of a scientific meeting, so somebody's going to give a presentation about their work. So let me briefly go to the agenda of today. So first we're going to have the presentation by Gerald from NXP about the Drone for Bats project. And that will take about 20-30 minutes, kind of depends, of course, on the presentation. Then so just Q&A discussion based on the presentation will be held after that. And after that, I'm going to share a poll to have a topic selection for the next developer technical meeting of the 21st of June, which is also on the Wednesday. So yes, I will stop sharing my slides, and Gerald, you can start sharing yours if you can.
Okay. I hope it's doing the right one. Yep. I can select the other one. Do you see my screen?
Yes, I can see your screen.
Nice. NXP Mobile Robotics. I will first introduce myself. About me, I'm electronics engineer working with NXP since 1995, so more than 25 years now. I'm an RC model pilot since I'm young. So my father founded RC Model Club in Austria, and personally flying drones since 2014. And then I realized that NXP likes to do something on drones, and then I shouted out, "Hey, I know something about drones. I like to contribute there." Meanwhile, I'm allowed to do that full time since 2020. Before it was just part-time contribution. I'm in our team leading development projects, public funded projects, internal projects in the mobile robotics domain. Having some students here in Hamburg working for me. I'm also the only one NXP test pilot, the official one. So besides building drones myself, testing it, I'm also allowed to fly it. I'm also representing NXP at the UAV DACH lobby organization. That's an European drone lobby organization. Also being part of the German government Drohnenbeirat, so the drone discussion group within the German government. And I was recently announced as a member of the director of boards of Drone Code Foundation, and I'm here part of the ROS Aerial Working Group. That's about myself. Some words about NXP. NXP is one of the big semiconductors manufacturers, acting in several domains: automotive, industrial, mobile, smart home, smart city, communication infrastructure. So we are a worldwide company in more than 30 countries, more than 34,000 team members, as it is called now, headquarters in the Netherlands. So we are still a European company. Yeah. Also one of the big players, I have to say, but don't spend that much time on that. Go straight into mobile robotics, where I will show you the components we are using in the project, that you understand, okay, based on what components are we doing the development, and what are we using for then playing on the software side with ROS. When we looked as NXP at a mobile robotics device system block diagram, we have a bus communication nowadays. In the past, it was more, we have UART communication between devices, point to point. Now it's going towards a bus communication utilizing CAN bus, also Ethernet. And having that in mind, we started with developing solutions. So we are just a chip manufacturer, but our experience is to motivate people. You also need development boards in a certain form factor and customer can directly use to play with. Usually, a company like us does big development boards, 30 by 30 centimeters, an OEM can work with, nothing an end user can work with. That's different here for mobile robotics. We are doing a lot of custom designs, small designs that should be able to fit directly into a mobile robot, ground-based, airborne, or on the water, whatever you can think about. So we have done CAN node interfaces, we have done companion computer, vehicle management units, Ethernet switch, motor controls with third-party battery management systems. That's where we are. And those are the components we are mainly using in our projects, and more details on that. We are just working on the success of the current flight management unit, which is drone code PixHawk standard alike. So PixHawk 6 design it is, if I'm not mistaken. But then with an gigahertz M7 MCU with a secondary M4. Also, and that's important for us to promote also solutions we have for communication. So we use T1 automotive Ethernet besides normal Ethernet. I will come to that later again, why. We have also free canvas. We are enabling PX4 on that with Natix, but also Zephyr as an real-time OS, and for example, Cognipilot is also ported on that hardware. That's for the flight management unit. We also have developed a mission computer, which is based on our NXP IMX 8M Plus. That has also a machine learning 2.3 TOPS MPU accelerator directly in the micro included. We provide an Ubuntu-based or Yocto-based Linux with Ubuntu proof of concept overlay with ROS2. Yeah, so you can download a ready-made image. Latest is Ubuntu 22.04 with ROS2 included. And this hardware is also listed as one of the official companion computers for the iRobot Create Free, so it should be well known meanwhile to the ROS community. We have dual Ethernet on there, 2 USB CAN ports we have directly on the companion, which is giving us some advantages. For example, to drive ESCs directly from the companion, not having the need of having flight management or flight control sometimes in between for driving ESCs via canvas. We also have made an Ethernet switch for T1 Automotive Ethernet. What is T1 Automotive Ethernet? It's 2-wire, just simply 2 wires unshielded, and we can run 100 Mbit over that one. So it's coming from the automotive industry, used in cars, modern cars, for the internal communication besides campus, so for everything where higher data rates are needed. T1 automotive Ethernet is used. Very lightweight because no shielding needed, and therefore we see this as a great advantage for especially flying mobile robots because their weight is flight time. What else? Battery management board. So in the automotive industry, battery management is also a huge topic for the electrification, and we are using such an automotive cell controller directly on a reference design for drones. So we have made this battery management board that can also talk drone cam, by the way. I'm actively using that in the project. Um, and does also cell balancing. So that's very important for our project I'm talking later about, because we need to charge the batteries in the vehicle. And this battery management board does also the charging control in the BCC, so in the cell controller directly. That's a huge advantage to us. What else? Yeah, usually you need to bring, let's say, old style sensors with I2C, SPI, or UART to the canvas nowadays. For this, we have done this UV-CAN node board or drone-CAN node board. We have also enabled PX4 on this, so there is a PX4 target available for that one. And you could run maybe a distributed system with PX4 or do your own development based on this. Recent release is this, we call it CanHub K3. It's a very flexible development or reference design, making use of an automotive ASIL D functional safe certified microcontroller. It has a lockstep core, so two cores, one running in shadow, checking the code execution of the first core and flagging if in the code execution something has gone wrong. It has 6 CAN transceivers, so you could also think of maybe media conversion from automotive to via Ethernet or to Ethernet to CAN bus or vice versa. We also have made some special transceivers on that, like a signal improvement where you could do a star interface with the CAN bus, or secure CAN where you can flag CAN messages that are not belonging to the communication currently running on the bus. For example, to indicate if someone tries to do an attack on the campus, something like this. It also has UART for UARTs, I2C, SPI, and also PWM headers, so 8 PWM outputs. And it has an IMU connector. I even have used this board as a flight control on one of our drones. We have also enabled PX4 on that one. So it could be used also in a ROS environment as a flight control or a safety flight control. Those are mainly the components. Beside our own developments, we are using also third-party solutions for the project based on NXP silicon. For example, 77 gigahertz radar sensors that are coming from the automotive industry. That ones we use for obstacle detection on the train. And therefore, also the need for having a high bandwidth communication on the vehicle with T1 automotive Ethernet, that we can put the data very fast from the radar sensor on the companion computer. Also, ESC design has been done with a partner company based on an automotive grade micro with dual CAN bus, up to 12S supply and 60 amp continuous current. That one is used in the vehicle as well. And ultra wideband. Some words on ultra wideband. Ultra wideband is a technology running on between 6 and 9 gigahertz. There are 3 channels on that. And with ultra wideband, you can do precise localization. So distance measurement by time of flight. And also our model is capable of doing an angle of arrival measurement. So we can also measure in 2 axes where the signal is coming from. I will tell how we use that a little bit more on the next slides. So those are the solutions. A little bit information on our history in projects. So we have already done several projects or running several projects. We had with German DLR, so the Airspace Research Institute in Germany, a project on airspace integration. We used our communication systems for e-registration because of security, hardware security we have available. We had another airspace management project recently here in Hamburg. We had the other Corsa project, which is just finalized, where we looked into functional safety for drone and made a functional, safe, and secure drone reference design. And we, beside the Drones for Bats project, I will talk later, we have the High Connects, where we look into 5G communication development, but also use all the components I've shown before for setting up on drone. It will be, for this project, a 25 kilogram drone octocopter with 2.5 meter motor-to-motor dimension. That is our history and what we are working on in general in projects. But a little bit more info on drones for bats, because that is the current project where we start using ROS2 for airborne vehicle navigation. What is the project all about? In principle, there's always, if you talk about green energy and new energies, a challenge between the green power and saving protected species. Especially in Germany, you could run into troubles there. And one of the challenges the wind power industry is having are bats. Why? Bats are protected, but bats are flying also in areas where wind farms are set up. And this project tries to address this challenge and tries to develop an improved solution for detecting the bats within the wind farms by using drones. That's what we are doing in this project. It's a 3 years project, already started 1.5 years ago, or 2 years ago, meanwhile. Will still run till mid of next year, and we have done already some developments I will show you later. The challenge there is that evaluation of a bat is done with an ultrasonic microphone, which has a range of 30 meters. And bats are flying up to 10 kilometers high, and wind turbines have a height of up to 240 meters. So the measurement at the moment is taking place by an evaluator on the ground. And as you can imagine yourself, the measurement is most probably done at the wrong spot, on the wrong place, because at 30 meters there is no issue. The windmills start at 40 meter height, the rotor blades going up to 240. The issue is, at least in Germany, after the evaluation has been done, and the evaluation is done over periods where bats are flying, and bats are flying usually throughout the year between April and October. Evaluation is done before a wind farm is set up and right afterwards. And then the wind farm operator is getting shutdown times for every windmill, for every individual day based on the evaluation. And that's not ideal, what is happening at the moment. And they like to get more energy out. And therefore, we think with using a drone, doing the evaluation, we get improved data. That's what we are doing in the project. What is NXP's task in there? Our task is development of a full autonomous drone, so no operator on site. So the drone should be located in a wind farm, should have an automatic charging at and landing pad. We should be able to precisely land on this pad with the right orientation, because as you see on the picture on the left-hand side, we have charging contacts and we have two poles on the landing gear, plus and minus, and we need to set or land directly on these contact plates to be able to recharge. Also, the mission execution should be done based on the weather conditions and position and orientation of the wind turbines to be incorporated. The wind turbines are moving towards or into the wind direction. So this means we do not know exactly when we set a mission how the orientation of the windmills will be at the time of the execution of the flight task. Therefore, we were planning to incorporate the full functionality into ROS2 to be able to be very flexible with all the tasks and needs we have. The requirements on the autonomy are that we take weather conditions into account as well as vehicle healthy. So part of the ROS2 flight stack or mission execution will be that we get weather data and check before takeoff, are we in the condition window we have. Bats, for example, are not flying at wind speeds, and I need to lie, I don't know exactly. I think it is 7 meters per second. So if wind speed is below 7 meters per second, then bats are flying. Bats are flying when the weather is dry, so they're not flying when it's raining. They are flying only at temperatures higher than, I think it is 9 degrees, but I could have mixed it up with the 7, so that it's wind speed 9 and temperature 7 degrees Celsius. But yeah, don't hit me hard on that. We have dynamic geofences, no-fly areas. So as I stated before, the windmills are turning into the wind. There should be waypoints predefined, and missions should be executed automatically. So in principle, drone should take off if weather conditions are okay, should fly to the measurement point, remain there for maybe half an hour, do the ultrasonic recording, next waypoint, do the same when battery is empty, return to the landing pad, recharge, do the next mission or the same mission again. Something like this. So in between the windmills could turn, wind could turn, come from a different direction. All of that we need to incorporate. What we will get, at least from the wind farm operator, we will get the orientation of the windmills in real time, but we need to upload them during runtime and check if the data are correct. Also, to have an additional safety net, we need to incorporate the point cloud information of the radar sensor. So therefore, we've used radar sensor. One important thing I have forgotten to mention, bats are flying only between sunset and sunrise, so during night. Using optical systems, cameras will not help. What we could use are LiDAR sensors. Yes, true, but we also like to promote NXP technology, and we don't have LiDAR technology as NXP for chips that are used on the LiDAR sensor. Therefore, radar is set, but we need to test if it's working. I mentioned landing always on the charging bed, very important. Also in case of battery empty, we need to return to the charging bed. So means also remaining battery lifetime calculation is important and need to be done within the ROS environment. So also the safety functions need to be reflected in the ROS environment. PX4 provides already some safety functions, but besides, worst case scenario, battery is dead, we land where we are. No other automatic functions of PX4s are allowed to use because that would give a risk that we fly straight into a windmill, as PX4 doesn't deal with radar sensor data. We are only able, or point cloud data, we are only able to do that in the ROS environment. And we need to work with scheduled waypoint and mission execution. So as I mentioned before, mission execution, return, recharge, vehicle is healthy, weather is okay, take off again. And we need to be able to update also the waypoints dynamically or the flight path dynamically. Those are the requirements we have. We have done already some pre-work. We have tested some navigation functionalities, collision avoidance functionalities. This has been tested in the previous task for a project, but now we need to put all of those together into one big system that is capable to execute the full mission. Just some word on how the things are connected together. What we are using as a flight control is the Arterian Sky Mode. And we have our main companion computer, the NavQ Plus, based on the IMX 18 Plus, here that is connected via Ethernet. So main connectivity between companion computer on the left-hand side at the moment, so that's the state of today, at the moment is via Ethernet. Via the Ethernet switch, we have also an additional companion that does 802.11p communication. We have the battery management system connected via CAN bus to Skynet. We have an ultra wideband sensor connected via UART, and we have a radar sensor connected via T1 Ethernet. That's the setup. The full setup as it should be at the end of the project, that we have also an additional power distribution board, power switch in between connected via CAN that can do parachute release, can switch off the ESCs. All of those safety functions should be included there, and there the S32K3, so this CAN-hub K3 board will be used to drive these functionalities there. Oh, I missed the Ethernet connection. That one will have as well. That's how the system or the vehicle internal setup will look like. And as mentioned, we have done already some pre-work and some tests, but now the big ROS work will start. What have we done so far? And I hope the video is working on your side. So the drone is flying already. First test flight, manual mode. We have also done mission mode with PX4, full autonomous. And we have tested the radar sensors, and I will stop the video here. What you see here, the drone is flying next to this tree line. And you see here the point of the radar sensor data as ROS point cloud. So we were sending that over a Wi-Fi link to the ground station, having RBIS there on a computer on the ground. And these are the points the radar sensor is providing. So the radar sensor manufacturer has made a ROS2 driver for that, so directly providing point cloud information. That's very useful to us, and therefore we have decided to go for this radar sensor. Three colors are seen there. Yellow is a vertical mounted one, so the yellow dots is the ground. Blue ones are this tree line, and there are some red here, and those are the three sensors I initially had mounted. So two left and right looking horizontal, and one in the middle looking forward vertical to have also kind of terrain following radar. In the pictures before, you don't have seen three sensors, just one. Yes, I have moved back to just one sensor because of weight. One of these sensors weighing 200 grams, and therefore I've decided to reduce weight to get more flight time. And now we have just one sensor because in this project we will do a proof of concept. So is a radar sensor working good enough for such an airborne vehicle? Then one is more than enough. Yeah. The next thing I've mentioned, ultra wideband and precision landing. For us, it is very important that we can land precisely on this landing pad. And we like to use our ultra wideband technology for that. That's another test drone I have. You see here an ultra wideband system mounted on the drone. And we have also one ultra wideband system on the ground. So as mentioned at the beginning, our ultra wideband system is able to measure distance as well as angle of arrival. So we can do with just Pythagoras sentence calculation, we can calculate a relative position related to the system on the ground. And using that with the precision landing functionality PX4 has built in. So at the moment, we just use the functionality of PX4 that was initially based or is initially based on the AR log, so infrared beacon for precision landing. We have adjusted that to work with our ultra wideband system. In the next step, we will go towards ROS, that we have also a driver in ROS and do the whole functionality in ROS as well. Because PX4 still uses them for executing reaching the desired set point GPS. So GPS inaccuracy is still playing a little bit of role at the execution at the flight maneuver. Position calculation is done based on ultra wideband, but executing then the corrective flight maneuver still GPS is used, and that we'd like to overcome by moving towards ROS in the future. Also showing that video, that is a test of the ultra wideband precision landing functionality. You see this orange dot here. That is the landing target. There is a black box on that one, which is the ultra wideband system on the ground. I have the ultra wideband system here at the front of the drone. And that's me, by the way, the guy with the yellow jacket. The drone is doing the landing full autonomously, and you will see maybe at the end of the video, the remote control at that moment was laying on the table there. I don't know if it's coming into the view. Yeah, here. And the drone executed that task full autonomously, just guided by ultra wideband. So we are very confident that we can reach our goals there. That's it about our hardware and our work we will do in ROS. A lot to do still, but we have done some pre-work. We have ROS drivers for the radar sensor. We have done already in the past collision avoidance in ROS 3D. And now we need to put everything together, but with the focus that we like to do NAV2 in future, maybe going first into a 2.5D navigation, that we say, okay, we try to solve the problem just on one plane. If we can't solve it there, move up or down horizontally and try to solve it there. Unless in the meantime we get real 3D navigation into ROS2, NAV2, but I doubt that this will happen in the next year. Let's see. That's my presentation. Thank you for listening. Any questions?
Right,
Thanks, Gerald.
thank you. Thanks a lot. Yeah, so if anybody wants to ask a question, just turn on your microphone and say it there or say it in the chat. It's up to you.
It's pretty cool. Thanks for the presentation. I really appreciated all the details and stuff. I was actually curious on when you get to the ROS2 stuff, are you doing all of that internal, or are you going to be doing any of the ROS2 work open source? I know like the Smart Micro has their open source ROS2 driver, but there's other parts of the ROS2 stuff like the path planning.
Okay.
Yeah.
So our goal is that all code we will produce in the project will be at the end open source. We cannot guarantee that it will be immediately, because usually we have a process internally that we need to run through approval before making something public. So it might take some time until it gets public, but all the work at the end should be open source. Yes.
Very awesome. Thanks.
Any other questions for Gerald?
I have a question for you, Gerald. What sort of gaps do you currently see in the software stack, right now as a hardware manufacturer? What is missing out there so we can support you better as a manufacturer?
Hard to answer because I'm not the software guy. I'm a technical engineer, more the hardware guy. But my understanding so far is one of the biggest problems we have is the interaction between the ROS system and flight control system that should do then maybe the safety tasks. So that's always the biggest problem, because on both ends things are changing over time and you're starting development, and in the meantime things are completely different on the other end. That's one of the challenges. Also, yeah, I mentioned it already in the last meeting, simulation. Setting up a simulation environment is really challenging. From the software side in general, so if a hardware manufacturer like us is sticking or checking which are the software bits and pieces used by the community and sticks to that, then it's no problem. So for us, it was relatively easy with putting the Ubuntu overlay on top of our Yocto build to integrate ROS2. So there are, even for the ARM architecture we are using, everything is there. The only challenge is then, yeah, for hardware, specific hardware we are using, like cameras, yeah, that a driver is available for the ARM architecture. But everything else, if I look at the ROS environment, is not that big problem. So.
Awesome. Thank you so much. That's a great answer.
Anybody has anything else? Or else I have another question myself. Like I'm not an outdoor drone person, so this probably is going to be maybe perhaps a bit of a stupid question. But I've noticed that you used also for like to aid, I guess, the GPS localization bit to make that a bit more, or like the positioning a bit more accurate. You use ultra wideband. Why ultra wideband and not R2K?
Because it's our technology.
Oh,
And we like to promote our technology. That's the reason. And the other thing is the experience having discussions in the previous projects about UTM integration, especially in urban environments. Even with RTK, if you fly between buildings, you get a problem, yeah, with the GPS signal. Think about urban areas where you need to land between tall buildings and signal is covered by these buildings. So there, that's something we got asked several times to, is there a solution for a ground-based navigation system? Yeah. Another use case we were asked several times is landing on a moving platform. Yeah. Ship deck landing for people that are mainly landing on gray painted ships. Let's phrase it like this. Those people are heavily uh, relying on a precise functionality for landing of their autonomous systems. And I haven't included it in this video, but we are also able to land on the moving targets by ultra wideband. We have done it. I'm having a video on that. If you're interested, I can still show it. But yes, the solution is very precise. You can even use it for landing on a moving target. And that's the advantage we have besides GPS.
all right. Yeah, I guess like ultra wideband. It of course depends on which mode you use it, but it is not completely. How do you say it's? I get like it's the things that are in between the signals or like the beacons are still going to be a little bit affected. Like if there's some kind of metal or things like that. At least that's.
Yeah, there are two modes. There is a two-way double-sided ranging where you have two or up to 5 dedicated partners that can talk to each other.
Mm-hmm.
And there you have a very high precision. So at the 10 centimeter accuracy or below 10 centimeter accuracy. And
That is very good.
angle accuracy 3 to 5 degrees. It's more than enough, and that's what we are using for the precision. And there's another operational mode, time difference of arrival, and that's something where you could use several hundred, I don't know how many devices, because there you have a network, a fixed installation network. The fixed installation is sending ping signals, or similar than GPS, sending out beacon information with timestamps. The devices on your robot are receiving those signals, and by the time difference of the timestamps, you can calculate the distance and then with trilateration your position. This mode is a little bit more inaccurate. So I think looking at what is available on the market, all the solutions that are there have half a meter accuracy. So that's less than RTK.
All
But
right.
good enough, you can increase the accuracy by placing your anchor smart, yeah, at different heights, different positions, then you can increase your accuracy. So even with such a system, in the past, we have reached the same accuracy because we have used multiple anchors at different heights. Even with that one, we were able to land on a moving target. But the use case for this is more, yeah, GPS denied zones, navigation, indoor navigation, something like this for ground-based vehicles.
All right, thank you for the explanation. Okay, if there's no more questions, of course, anybody can, of course, contact Gerald directly if you have any questions afterwards. But I'll just share my slides again because we have a couple of more things to finish up for the meeting.
Thank you.
And of course, Gerald, thanks a lot for this presentation. That was very interesting. All right. Okay, so I think one of the things that we also would like to do here is to select a topic for discussion for the next discussion or developer meeting. So I've prepared a poll and I'm going to launch that right now. So if anybody can vote on which topic they would like to discuss about in 2 weeks, please place a vote. Or if you're not agreeing with these topics, please suggest perhaps another one, and then I'll add it to the list for next time. Anything that we've already discussed in the last 2 developer meetings, I haven't put in there. So so we have 4 votes so far. Yes.
Is there somewhere a voting functionality, or do you expect just a message?
No, it's actually, there is a voting functionality. It's called a poll, and I think you should have gotten a message by Google Meet, or perhaps you have to go to the
on the bottom side, on the bottom navigation bar next to the chat icon, there's an icon with the triangle, a square, and a circle, and then you have to click polls. Hey everyone, I need to go because I have another community meeting happening soon. But thank you so much for your time today, Kim, and thank you for your presentation, Gerald. I'll talk to you everyone soon, and I hope that you can join the PS4 Q&A soon. Goodbye.
Bye. All right. I think we have 8 votes by now. I'll place my own vote also. I think we got all the votes for now, so I'm going to end the poll. I'm not sure if everybody's able to see the results, but as you can see, is that swarm communication has won a discussion topic for next time. So I'm just going to save all the other topics for items for, of course, another time or another poll. But in 2 weeks, we're going to discuss swarm communication. So the next meeting, developer technical meeting, is going to be again on Wednesday, 21st of June, 2 p.m. Universal time, coordinated time, UTC. And also, I would like to remind everybody on the GitHub organization for this working group, which is github.com ROS, not slash, no dash, Aerial. You can see it right here. So we have the Aerial Robotic Landscape, which pretty much I have the list of topics from. You can just add an info page if you like. I am currently the only contributor here, but it would be nice if anybody else could, of course, join me in adding the information. And also the community repository, add yourself as a member to the README there. And of course, if you would like to do a presentation too, which should be in like a month's time, so that's the first meeting of the July sessions, then send an email to me or Ramon. You can see the email addresses right here. So yeah, I think that is it for now. Is anybody that wants to have has something that they want to announce or just like a final question, then now is the time. I guess not. So I would like to thank everybody for joining this meeting, and I'll post the recordings as soon as we can. So yeah, thanks a lot. And thank you, Gerald, again from NXP Semiconductors for giving such a nice presentation.